Okay, so now that we've talked about the mechanics of division here and rewriting the polynomial using the quotient, divisor, and the remainder, let's see a couple of other things we can figure out and determine. So a little bit of theorems and theory here. So we just talked about how the polynomial can be written, and right now we're going to talk about dividing by something of the form x minus c. So the polynomial then can be written as, let me get a color here. It can be written as x minus c times the quotient plus the remainder, kind of as we said before. Well, let's see how, let's find p of c. So in this form, we have this general form of the polynomial, p of x equals above x minus c times q of x plus r. Well, say we wanted to evaluate what the y-coordinate of the polynomial was at c. So I would say p of c equals q of c, I'm plugging in c for x, times c minus c plus r. Well, because c minus c is 0, and 0 times anything is 0, I'm going to get 0 plus r, or r. In other words, that the y-coordinate of the polynomial at c is the remainder when I divide the polynomial by x minus c. So in other words, p of c equals remainder when divide by x minus c, which is kind of weird to think about. And I'm going to give you a visual perspective soon of this, of why this makes sense, but let's first talk about these theorems. The remainder theorem, if a polynomial p of x is divided by the quantity x minus c, then the remainder is equal to p of c. So I can find the remainder when I divide by x minus c by simply finding out what the y-coordinate is of the polynomial when x is c. So in a factor theorem, and this is going to be big this is the whole point of this factor theorem, is we would ideally like to find something that's a zero of the polynomial, meaning that it divides in evenly. So if x minus c is a factor of a polynomial, then that means that p of c equals 0. In other words, c is a 0 or a root of the polynomial. It divides in evenly. So that's a really important one. We're hoping to find something that is a factor, and therefore that gives us one of the roots and helps us to break down the polynomial further. Okay, so let's talk about a visual perspective of this remainder theorem. Like, why does it make sense that the y-coordinate of the function at x equals c is same as the remainder when I divide x minus c? So I'm going to draw a little axes here. Now, remember, if x minus c goes in evenly, then c is a 0, right? So there's no remainder. Then it would be, c would be an x-intercept. So if I think about, here's c, and c is not an x-intercept, so here's p of c. Well, this y value here is, we can think about it, is how far off is the graph from being being a 0. So how far off is the y-coordinate from 0? And that's the remainder. How far off is my function from dividing in evenly? So in other words, you could think about it for x minus c to be a factor of p of x, we need to move p of x down p of c units. We would need to move it, in this case, if I'm looking at my visual, we'd need to move it down that y-coordinate when x is c. So and the graph is, if we're looking at this particular graph, it's saying it's too high for x minus c to be a factor. Well, how high is it? It's p of c high, or in other words, the remainder. Okay, so that is the remainder theorem. Again, the remainder theorem says that when a polynomial is divided by x minus c, then the remainder is the y coordinate when x equals c. All right, so let's look at, let's find a good one to look at here that I can do. Let's, I want to figure out what's a good one for us to look at together. Let's look at the last one together, because I think this is kind of the crux of this whole situation. A lot of it is, a lot of this you're going to see is just practice. Both using synthetic division and long division. Again, synthetic division, you have to have x minus c be, the divisor has to be of that form. Okay, so let's look at this last problem here. So this is what we're essentially getting at. We're getting at this function, and when the polynomial, and I'm saying consider the function p of x, and first I give it to you in factored form, and then I FOIL it out. When the polynomial is expanded from the factored form, the last term 24 is equal to -2 times -3 times +4. The zeros of the polynomial are all factors of the constant term 24. Use this idea to factor this different polynomial and sketch its graph. So in other words, what this is saying here is if I'm able to put this into factored form, then the zeros in this case, because I'm starting out with a coefficient, a leading coefficient of 1, I can think of the possible zeros as being factors of 10. So that means I could try ±1, ±2, ±5. Okay, so let's see which of these, and to see if it's to see if any of these are zeros, it's literally just trial and error. Let's plug it in and see if we get 0. Well, kind of because I've done this before, I know that -2 will give us 0. I get 16, and I'm going to get +24, then I'm going to get -44, -6, +10, which indeed equals 0. Okay, so I know that because -2 is a 0, x plus 2 is a factor of p of x. Okay, which means it divides in evenly. So let's see what we get when we divide -2 in. Well, and I'm going to do this using the synthetic division because I have a divisor of the form x minus c. So I've got my -2 as my c value, and then I'm going to put the coefficients of the dividend, which is my polynomial, 3 and 10. Bring down the 1 and multiply and add. Keep doing this algorithm over and over, and then -10, which is what I expect. Because I determined it was a 0, I better get a remainder of 0. All right, so what I just figured out was p of x equals x plus 2, my divisor, times my quotient, which is going to be x cubed minus 5x squared minus x plus 5. Now, because I'm not down to a quadratic, I could, many times I'm going to have to do this whole process over again, this time figuring out if any factors of 5 are a 0 of this further broken down polynomial. But I'm kind of noticing that I can factor this bit by grouping. So if I put these two together, I should be able to factor by grouping here. I got p of x equals x plus 2. And then if I take out an x squared, I'm going to get x minus 5. And if I take out a -1, I'm going to get x minus 5, which is exactly what I wanted. So p of x equals x plus 2 times x minus 5 times x squared minus 1. Or in other words, we've got p of x equals x plus 2, x minus 5, x plus 1, x minus 1. All right, so now I have everything to be able to sketch a graph here. And notice I have 4 zeros, all of multiplicity 1, which means they're all going to go straight through. Multiplicity is the exponent, they're all raised to. And so let's see, I'm going to put a 0 of -2, a 0 of -1, a 0 of 1, and a 0 of 5. And let's eyeball the initial polynomial, which has a leading term that has an even degree and a positive leading coefficient. So the end behavior should be up, which is enough to give me an idea of what's happening. And I know the y-intercept also is 10, so kind of up here. So my graph is going to look like something like this, the general shape of it. So that's putting everything all together. And there's one more theorem we'll talk about next class to figure out how exactly what's the ways I can test the possible zeros by trial and error to figure out if there are any rational zeros, and then in order to be able to use synthetic division and break down the polynomial. But that'll be next time.